So, what can we do when we have a partial or uncompilable source code and we cannot use compile, use IDA, and then diff? So we can either build the small parts to object files, each CPP or zip file or whatever, and then importing them, but it's tiresome and it doesn't properly work because most of the time the files that you cannot compile are actually the most interesting ones. Or someone writes a tool for doing it and we don't have to do that. I'm a bit masochistic in the senses, and it was for me a very interesting computer science problem, and I decided to write a tool for that. So when I started having that idea was when I was researching on a nameless security product, an AV, and I realized that there was a big source code leak that happened more than 10 years ago. So I downloaded that leaked source code and tried to build it. There was no way to build that source code. Also, I didn't have many of the headers that were required. I didn't have many of the libraries that were required. The compilers used were dated from more than 10 years ago. The only files that I managed to compile were very small ones, the ones that I really didn't care. So I ended up trying to port symbols manually using my brain, and that's it. So things like, okay, I will find that string constant in both the source code and in the binary, and if a function match because the string is only referenced in this or that function, I can rename it myself in IDA. Then also finding nearby functions, and after a while I said, this is stupid, I automate it somehow. So I opened my to-do list, write the idea, and 2-3 years later I started working on it. So, the tool. As I previously explained, I started working on this tool, named Pigaios, which is Greek for source, as in source code, in 2017. The very first rudimentary version or prototype of the tool took me around 1 month to write, mainly because I didn't have any tool or framework to work properly with source codes as we have IDA for working with binaries. After I had a very basic, pretty basic and rudimentary framework for working with source code, I called extract things from the source code and start comparing things. Okay, so how does such a tool work, like the one I wrote? So basically what we need to do for porting symbols or diffing, matching functions between source codes and binaries is to parse the binaries. We can do it easily with IDA, as well as we have to parse the source code. This is a bit more problematic because there is not such a tool like IDA for source codes. Then we extract themes, artifacts for each function found in its function source code. We extract the same artifacts for each function found in the binaries, and then with the artifacts we extract, we just match them. We compare, and if the artifacts are the same or similar, it is a match. And then, this is a part that is not funny because it's pretty hard, we calculate an accuracy ratio. That's it, how similar or how related are both functions that we match. And basically, this is all the tool does. It's a bit more complex than what I say here, but basically it's only what it does. So parsing. As I said, we can easily extract information from binaries using IDA, but unfortunately there isn't anything even remotely close to IDA for source code. The most similar thing probably is ST-Tools understands. Some people here I'm sure that uses it or at least know that tool. But it's not even remotely close to what you can get from IDA. So parsing source code is the first problem that I had to somehow solve for me. So some people believe that parsing source code is an already solved problem because we have compilers and stuff, but it's far from being a solved process at all. So yeah, we can parse one dialect of whatever language we support or we want to support, if we are writing a compiler, and that's all. But in our case, we want to support any and all dialects of any of all the languages that we want to support. In my case, I decided to stick to C and only support the C language for now. But still, I mean, only supporting the C language is pretty hard. Why? Each compiler behaves and supports a very different subset or a very different dialect of the C language. Some of the things that are more different between compilers are, for example, compiler extensions. Some things that came to mind quickly, I wrote it in around maybe 20 seconds or something like that, are pragmas. Pragmas are in support by all compilers, and each compiler implement them in a different way. Precompiled headers. So if you include a precompiled header using the Microsoft compilers, you can write whatever you want and input binary data before you include the precompiled header. Of course, it is not supported by any other compiler but the Microsoft compilers. Another thing, omitting the middle operand of a ternary expression. So we have X, interrogation, nothing, point, Y. This is an extension that is only supported by GCC. Embedded assembler differences. For example, if you write embedded assembler for the Microsoft compilers and for the GCC or CLang, it is totally different. Switch case ranges, out of class definition of static cons integrals for the new members, which is only supported by Microsoft. Finally, what we end up is writing ugly workarounds for each compiler that we want to support when we are coding, and when we are trying to parse them, we are actually doing the same, using ugly workarounds to support that specific feature of this compiler or that compiler. And also even trying to work around compiler bugs. That thing might be rare or weird for you, but it's not. If you don't trust me, try searching, doing any of the searches, for example, in GitHub, and you will have tons of results of people having the same problems. So, how can we parse source codes? For example, for my first prototype, I used PyC parser. Oh, sorry. Maybe you know. Maybe you know it. It's a Python library for parsing C source codes. It is good enough for a quick prototype or for a use and throw tool, but I don't recommend you using it for anything half serious. Another option is using Flex, Bison, NTLR, Rage, or your own one tool to parse, to write a parser for the C language or whatever other language that you have to support. But your project is not whatever you want to do anymore. Your project now is writing a parser. So I don't recommend you doing so. Another option is like the people from ST-Tools understand, or Fabian Yamaguchi did, to write a fuzzy parser, like Joxean. So it's basically like the prior option. Your project is not anymore writing that tool that you have in mind, but writing a parser, but with less rules. I don't recommend any of these options. Another one, if you hate yourself, it's using GCC XML or something related to GCC. Please don't. Also, if you have a rich uncle in America, or if you are in a university, you can maybe get a license for the Edison, the SyncGroup, C++ frontends. These are the de facto ones. Actually, they support different compilers and even different compiler version bugs. It is awesome, but it's not cheap. And otherwise, if you are poor, like me, the only remaining choice is using CLang, and either the bindings for Python, which is what I'm using, or the APIs for C and C++. So the good things of using the CLang Python bindings is that you have support for Linux, Windows, Mac, and FreeBSD. You get an abstract, syntax tree, and AST for each function, regardless of it having errors or not. Even if it is wrong, the function, or you lack some structure or some enum definition, it will still give you an AST. This is just what I want for that project. And also you get support for anything that the CLang frontends support. For example, now the CLang guys are working on the Microsoft Visual C++ extensions. That's it. It's supporting everything that the Microsoft compilers support. The bad things of using CLang is that, for example, the CLang developers don't really care about the bindings or the APIs. So every time you need to do something, forget about asking them or checking how to do it in a documented way, because most of the time they don't support it and they don't care. For example, let's say that we have an assignment like int I equal 2, right? We expect to have a documented way to get that integer literal value, the 2. Well, there is no documented way for doing so, and there is no exposed way. What we all end doing is we get that expression, we get the tokens, and we parse ourselves the tokens, which is not pretty, but it's the best we can do. So, extracting artifacts. So as I said, I'm using the Clang Python bindings to parse the source codes. We get the AST for each function, and then we extract things. Also, using IDA-Python, we extract the same artifacts, the same things from the source code and from the binaries. But what artifacts I use? Oh, just one thing. I'm using IDA, but one can use Binary Ninja or Radare or whatever else, as far as you can get these artifacts. So what I'm actually extracting now is pretty easy, which are string constants from the binaries and the source code. The number of loops, conditions, function calls, externals, and globals that a function have. The number of switches and their cases for each function. And if the function is recursive or not, because not all functions are recursive, so it is a good indicator for some matches. And also the list of calls. Not the list of callers, but the list of calls. That's it, the functions that are being called from the function that we are analyzing at that moment. I will later on explain why I'm not using the callers and just the calls. So, finding matches. Basically, when I extract things from the source code or from the binary, what I do is I create two SQLite databases, one from the source code and another one for the binaries, and then I perform SQL queries. This is the very first one, SQL query. If you check here, the only thing that I'm really doing is comparing the constants. The number of constants is that. This is the string constants in a JSON object. I check that it has constants, that the number of conditions is also the same or similar, that the number of loops is actually the same. This first query produces very little results. For example, when I was writing my first prototype, it only matches 90 functions out of more than 4,800 functions. It's pretty bad, or might look like pretty bad, but actually it's not, because those initial results were with 0 false positives, which is a pretty nice start, and from that I can continue digging up. So yeah, as I said, when you have near 0 false positives, we can then use these results, these initial results, and from then apply some heuristics to find more things. This is okay, this means that we have another problem. Yeah, but the thing is, the initial results, we know that they are pretty good, like very good. But the next results we are finding using heuristic aren't that good. So we have to calculate a ratio or something like that. So the reverser, when it's taking a look to the results that my tool outputs, can trust or not trust some results. That's not funny, I will explain later, because it's actually the hardest part in the project. So let's talk first about heuristics. All heuristics but one are based on the initial good results that I previously explained. And currently, the list of heuristic is the following one. The callers and the calls, that's it, call graph related heuristics. The nearby functions, specific callee shortest, and some rare constants. I will start, first. The heuristics are applied iteratively. What I mean with that, let's say that I have, like in the previous example, 90 functions that I found first. Then I apply the heuristic, and I have 5 more functions, 95. Then for this new 5 functions that I found, I apply the same heuristics until no more new results appear. Okay? Okay. So now let's start talking about each heuristic. So the first one, call graph matches, either for callers or for calls. So starting from a 1-to-1 match, the first good results that I have, I build the list of callers and the list of calls. I try to match each caller and callee from both and calculate some score to determine how good or bad the matches are. Then, for good enough matches, I save them in a temporary list. Then, after all the colors and collies are processed, I remove the bad matches, and only the good ones are saved and considered. If there are multi-matches, like I have Pantheon A and Pantheon A prime and B prime that actually match with the same result, the first result that I had is the only one that I maintain. Probably not correct, but I don't know what to do there. Nearby Pantheons. So this is another heuristic that is pretty easy. Let's say that we matched Pantheon Y and Pantheon Y prime in the source code and in the binary. Chances are that the Pantheon that is before the Pantheon Y, Pantheon X, is actually the same X prime in the binary. The same for the next Pantheons. It's a very easy one. A specific color shared. So the colors of a Pantheon in a code base and the colors in a binary can differ a lot. Let's say that, for example, we generate the SQLite for the libxml2 source code. Many of the supported Pantheons of libxml2 will have no color, but in the binary, of course, it will be called because that library is being used. So we cannot use the number of the colors, but we can use the collies because the collies is always going to be the same, or mostly, not always. So when I have a good match between the Pantheon X and X prime in the binary, I can check the colors of the collies of these both Pantheons because I know that it is already a good match. So the collies should be the same. Yep. Another one, same rar constant. This is probably the only heuristic that I've been able to port from Diaphora to Pigaios, which is I have one string constant, which is pretty rare. It only appears in one Pantheon. It is an awesome match. Even if the Pantheon differ a lot, that string constant that is rare enough, that is weird enough, makes the match that we have a pretty good match. Why? Because it doesn't exist in all the database. That's it. It's very easy. So, and these are so far the heuristics that I have implemented for this version of Pigaios. This heuristic finds many matches between source codes and binaries, but the quality of the matches greatly varies. And here is where another problem that I already briefly mentioned appears again. How can we rate how accurate or the opposite are the matches? I will talk soon about it. Problems. There are a lot of problems doing things like that. So the first one, porting symbols from code base to binaries is problematic. Surprise. So some of the many problems that I have discovered are, for example, control flow graphs based heuristics, the ones that I use in Diaphora and everybody uses in their different tools like Dynamic Bindifs or Darren Greens or Yadiff or whatever. Most of them are based on graphs. Cannot be used to compare source codes, especially from human-written ones to binaries. Why? Because the code that we write as developers is totally different to whatever generates finally the compiler. I'm not even talking when we are not using that, but ASTs from, let's say, the X writes the compiler. If we want to compare the ASTs, the abstract syntax trees from human written codes to the ASTs that the compiler gives out, the results are going to be funny. Another thing, which I call blind diffing. So in some cases, I use the compiler just to graphically display in either the match. So you can kind of diff the source code from the binary and the source code from the proper source code, I mean. But what if I'm comparing the source code with an SH4 binary, with an M68K, Spark? I don't have the compiler for that. So how can I diff that? Another, it is almost impossible to determine how much a function changed from the source to the binary. Like, we cannot know, because it can be a compiler optimization or a change that they made. It's pretty hard to know. Thus, it isn't easy, as I said before, to determine how good or bad a match is. So, control flow graphs. One of my very first ideas when I have the idea of writing such a tool on my mind was to use the Afora as to port many heuristics from the Afora to Pigaios. I quickly realized that it was a very bad idea because the control flow graphs obtained from source codes, especially from human-written ones, are totally different to the ones that a compiler optimizing generates. This is an extreme example. This code resembles an X server vulnerability back in the day, so the programmer made a mistake, and instead of calling getEUID, it simply checks if the address of getEUID is equal to 0. So the compiler says, hey, it isn't worth for anything. I will just remove everything here and put that. I will keep the call to getUID and the return. Puts OK. First, the functions are different. Put some printf, but that we don't care. But if we check, we have here control flow, but here we don't have control flow because the compiler just remove it because it doesn't make any sense to check it. It knows that it's not going to be 0, so just removes it. Okay? I repeat, this is an extreme example. Yeah.
You mentioned that the first thing that you take out is strings. So in this case, this would be.
Yeah, in this case, it will be actually a good match because let's say that the OK exclamation only appears in one function. It is a one-to-one match for me.
But you have a string that appears in the source and not the binary.
That's another thing, and I consider it. I reduce the ratio a bit. I will talk a bit later about that. So ASTs, abstract syntax trees. So as I said, ASTs from source code, especially from human-written ones, are very different to ASTs obtained with an optimized and the compiler, like the Hellraise one, that actually takes already optimized my binary matching codes. Actually, even for trivial functions, trying to dip source codes to pseudocodes proves to be complicated at least. So this is a one-to-one match. The only thing that I can match here is that call to xfopen for read. If I'm not wrong, this is BCBox. Do you see here? This is what the Hellraise, the compiler, gives to me. We have the while and everything. Everything that is in red or pink, I don't actually know what color is that. Is what doesn't match in the other part, but actually it's the same code. This is a non-extreme graphical example. This is another example, and it's another one-to-one match. We can see here that we cannot match the AST or the source or whatever we want, or even the control flow graph. This is a good match if we are comparing ASTs, but it is pretty rare that we have matches like that, and even in that case, check to the differences between the source codes and whatever the compiler gives to us. Another problem, as I said, blind diffing. So for visually diffing, for showing the differences, I use the compiler. As you can see here, doesn't make many sense most of the times, but well, we can get to see something. But what can we do if the compiler doesn't support the target architecture that we are working on? We simply cannot visually diff them. Makes sense? What I do is simply I show what I have matches from both functions, so the reverse engineer can determine or decide if it is good or bad. This is all I do. This is how the plugin looks. And for example, for this first function, which is a very good match, I say, so there is a similar number of conditions, and the constants, the string constants are actually the same, the number of switches, 0, is the same, and the number of calls is similar. By the way, look at how much, even for a good match, the things change. So in the source code, there are 10 calls, but finally, the compiler decided that you don't need to have 10 different calls in 10 different places, but only 5 calls in 5 specific places. And actually, and also the number of external functions or external things, references in that function is 12. So this is a good match for I think it was SH4, if I'm not wrong, and this is the only thing that we can do to show or determine how good or bad it is. So, calculating a similarity or accuracy radius. Once we have match, we need to determine how good or bad it is. For this, we need to create some kind of function that takes as input the source code function and the binary function and outputs a ratio from 0 to 1. I started writing by hand a function, compare functions, that assigned weights to each artifact matching as I thought it was right to me, looking to the results and changing and stuff. After a while, I said, this is horrible what I'm doing. I should do something more automated to calculate the weights. Well. And this is me doing machine learning and stuff. So, I started learning a bit about machine learning, deep learning, and all this stuff that many companies use as buzzwords for selling snake oil applications, with the hope that maybe I could do something for getting proper matches or a proper ratio. After various back and forths with different classifier algorithms, it turns out that no single algorithm, or even a mix of algorithms, was good enough as to replace my horrible and handwritten function. My final choice, after so many trial and errors, was to use a multi-classifier based on the following machine learning algorithms. So I use a decision tree classifier, an AB bias, gradient boost classifier, and a random forest classifier. So the first one, the random forest classifier, actually finds many positives, but generates many false positives. But using the decision tree classifier, most of the false positives that I found before are removed, and the other ones are mostly removed by these other ones. Okay? Okay. So it outputs pretty good results, in my opinion. As we can see, for example, talking about positives, in one of my datasets, from around 7,000 functions, it finds more than 5,000, which is pretty good, I guess. And the number of false positives is not that bad, just 0.161, which is very nice. But guess what? My very horrible function that I said this is not good and I have to drop it and replace with something more scientific is still the best. So now what I do is I use both. And I usually joke like I had one problem, so I use machine learning, and now I have two problems and I don't really understand one. So, yeah. So this is machine learning, but in any case, I finally added an ML column. So you know that the results from the machine learning algorithms are shown there. Here you have the ML. And the good thing is, if both my horrible function and the machine learning function tells you it is a good match, it is actually a very good match. So time for a demo. I will start with something easier. Yeah, sure. I was just getting to the directory, better that. So this is the source code of zlib version 1.2.11. The tool, I have to, 1 second. Yeah. So this is my tool. Source bindiff, I will probably rename it something. Minus parallel, minus export, it will parse the source codes, get the ASTs, and extracts from the ASTs the artifacts that I want. Let's launch it. It is running. It doesn't matter if it doesn't find some include file or some header files, or if something was wrong or whatever. Actually, it is showing some errors. I will show you. Here. Do you see the fatal? Because we don't have support for C++, and it is trying to include C++ headers and stuff. It doesn't matter, because we are already extracting artifacts, because we have the AST event for functions that we cannot compile. And then finally, yep, here is it. We can see that it says building the call graphs, building the constant table, and creating the indexes for it. Okay, so here we have our database, which is that one, zlib.1.2.11 SQLite. And now we can go to the binary. I will open item. And I will use that one. This is the mini gzip program from setlib, but from another version. And then I will run the script, the idle script, which is that one, that I will probably also rename source imp-ida. Okay. This is the dialog where we can choose the database, the indent command if we plan to visually diff things like CLang format or indent or whatever. Calculation ratio and display ratio, it is for internal calculations to consider it as a good match. And for display ratio, it is finally, after everything is calculated, what results are going to display from which level to. If we left it to 0, the default, I calculate myself what are the best values for this one. So let's say, no, BusyBox, no, that one, setlib. Well, we don't have too many results, but we have some results in this case. In another case, this is a very small program. So this is the first one, and here we have, for example, the function gset_red matches with the function at the address, and it says that the ratios, both calculated by the dirty function and the ml function, are 1.00, which is a pretty good result. We can show how it matches, and it matches because the number of conditions, the constants, and other things were actually the same, so it's a pretty good match. But diffing it, we will probably don't see anything that makes any sense. And as you can see, not even a single line matches. Yeah. Okay, this is the first demo, and now we are going to do another demo. This is BusyBox for MIPS architecture. We don't have the compiler or anything. And this is version, if I'm not wrong, 1.20 or something like that. Let me see. 1.20.0. I just downloaded it now, 5 minutes before the conference. And now I'm going to build, to parse the BusyBox source. Hey. This is where I have the source code for BusyBox another version, 1.29.3. I already have here the SQLite database, and I'm going to just use it to compare against a MIPS binary. I have used MIPS, but one could have used anything else, like, say, SH4 or Spark or M68K. It doesn't matter. It is absolutely agnostic of the architecture because we are not doing anything with the architecture. We are just doing things with some specific artifacts. So while it is doing things, it says that the decision tree, the ML, the machine learning-based system is available, so we can use it. It finds first 938 rows. This is the first iteration. This is what found that were good matches. And from the good matches, it starts applying heuristics to find more matches. And hopefully, it finds things fast enough so I can finish the presentation. Well, I will leave it here, and so later on the results. So the future of this tool. So the current status is production ready. Actually, I'm using it for my reverse engineering project. So trust me, it works. But I haven't had time to properly, I repeat, properly implement this part, importing structures and enumerations, which is the best part. Let's say that we've just matches 10 functors or something like that. But we can properly import all the structures and all the enumerations from that source code to the IDA database and apply the prototypes and save them. It is awesome. It is a lot of work that I don't have to do manually because manual structure reconstruction is a pain in the ass. I plan to maybe support Objective-C and C++, maybe partially in the future. Why? Because as I'm using CLang, it already supports that. Also, I don't think it will be a specific project. I think that I should just integrate in the Afora because it serves also a lot of code. And exporting to SQLite database, my idea is to take a lot of open source codes, export myself the SQLite database, put them somewhere in a web page, so you don't need to do that, and you only need to download the SQLite databases for your new project. You diff them, you import the symbols, and you don't have to care, and you can start working on your target, and that's it. Let's see if it finishes. Not yet, but well, the project is open source. If you give me like 2 minutes, I will make it public now. Make this repository public. Nah, it is fine. Fine, it is public now. And the demo. So, I will probably have to change my passwords, but well, we can see here, this is BusyBox, displaying many of the results that's actually found. We can see that it found here 1,000 results, which are actually pretty good, as we can see here, out of 3,000 functions in this BusyBox binary for MIPS, which is another architecture. And that's it. Thanks for your time.